嗯，好早，我今天很早哎。说子晴带枕头来，带枕头来，带枕头来，好吃。很紧，所以 Okay, all right. Welcome back. Next week we'll have the last quiz before we go into the final exam. Quizzes will be start from partial ordering up to graph. So this week will be mostly algorithm. So I'll just mostly read the slide and I'll show you some example. Okay. Any question for previous time? Okay. So let's recall from last time what object we studied. So last time we studied graph. Graph contain two data, one vertex step, second the hash. So if you uh, remove the simple circuit, what we obtain is we call the tree. Okay. So if we pick a root, okay, so let's here, and then we can turn this here to the tree, such that every vertex is directed away from the. Okay. Then today we'll learn a few algorithms to read how to systematically read all the roots, and then example of trees. For example, if you replace your vertex with atom, in this case carbon atom and hydrogen atom, then you'll get some chemical substances. And also you have your organizational chart or family tree, yeah, where you got secretary, treasurer, committee member. And also you have your file system. Okay. So in your computer, you got your file system where you can draw as a tree. And the root is the directory where the internal vertexes are the directories, and then these are the file. You also can use tree to record. Okay. So these are examples of trees. Okay. So so we call a rooted tree emery tree. Every internal vertex has no more than n children. And then we call the tree a full emery tree if every internal vertex has exactly m children. When m equal to 2, we call it a binary tree. So for example, the binary tree will look like this. So every internal vertex only have 2 child, at most 2 child. Okay. So this is a binary tree, but not a full binary tree. if you be full, you need to have 2 child for all the internal vertex. For full binary tree, you need to have exactly 2 child for all the internal vertex. Around it. Okay. Okay. So next. So next is ordered rooted tree. So ordered rooted tree meaning you order your children from left to right. Okay. So you count your children from left to right. And then for a binary tree, again, since you only have 2 child, right? So either you are left child or you are the right child. Okay. So in binary tree, we can call them left, right. And then uh if your child has another child, okay, so you can consider the left subtree. So all the subtree rooted at the left child. The subtree rooted at the right child is the right subtree. These are just some terminology. Later we'll do some more. Okay. Right subtree, left subtree. Okay. Okay, next. A tree with n vertexes has n minus 1 edges. Okay. When you have one vertex, how many edges you have for a tree? You cannot have one edge, right? Because if you have one edge, it will become a loop, which is a simple circuit. Okay. Tree, we don't want to have simple circuit. So one edge, one vertex only have 0 edge. Okay. And then if you have two vertex, okay, you want to form a tree. How many edge do you need? 2 minus 1 is 1. Okay. So you just make sure it is connected. So just to remind you, tree is what? Simple, connected, on simple circuit. Okay. So if you have n vertexes, you just need n minus 1 edges to connect them. Okay. N vertexes. Okay. Okay. You can prove by induction, but we won't do it here. You can go and check your textbook. Okay. The next one is a full memory tree with I internal vertexes contain m times 1 plus I vertexes. Okay. So let's try this. Draw the diagram. So what's the full memory tree? How many children do you have? Internal vertex. M, right? Okay. So for every root, for every internal vertex, have m children. Okay. So so the question is, what is the total number of the vertex? Total number of the vertex. How many? Okay. So the answer is m. Okay, m times I, number of internal vertex, plus 1. Okay, let us look at a smaller example, right? So when m equals to 2, and then this is the binary full binary tree. Yeah. How many internal vertex you have? 1, 2, 3. Okay, because these are the vertex that have children. So 3 times 2 is 6. But total number of the vertex is 7. So you need to add your root. 3 times 2 is 1, 2, 3, 4, 5, 6. So plus 1. 6 plus 1. N equal to 6. And so the plus 1 here is at the root. Okay. I won't prove this, but just let you understand. Okay. Everyone got it or not? Need another example. Got it? N plus 1. Where is this plus 1 from? It's the root. Yes. Okay. 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 Okay, next. So remember that last time we talked about the number of vertex, okay, is equal to the sum of the internal vertex plus the leaf. Okay, this one is last time we talked about. So the internal vertex and leaf partition the vertex. N equals to I plus L, where I is the number of internal vertex, is the number of leaf. So this one is have children. This one don't have children. Okay. Okay. Next. So there are some theorem on this emerald tree. So if you know that all the internal vertex have m m children with the total number of n vertex, you can calculate the internal vertex and the leaf. Okay. And then how is this coming from? This is the formula we did just now, which is n equals to mi plus 1. Right. So you can move the plus 1 over and then divide by n. And then you can find the internal vertex. Okay. What's this complicated thing about? So it's just using n equals to I plus L. Okay. So you already found you have your n, you found your L, and then you just take n minus this bit here, and then you'll get this. Okay. Okay. Need me to calculate or not? Or you can try. Can see or not? Let me calculate. This one you just take n minus 1 divide by n. And then this you take n minus this. So n minus this is uh, this thing here. Okay. Not very important, but some property of the full abbreviations. Can see it? Yeah. Okay. And then next, if I don't tell you the number of vertexes, I also can tell you the number of internal vertex. Okay. Then you also can play with this formula, you also can get the number of vertex and number of leaf. Similarly, if I only tell you the number of leaf, you also can get the number of vertex and the number of internal vertex. So this proof is just play around with two formula. So just use formula n equals to mi plus 1 and n equals. Yeah, just use this two formula and then move it around, you get the number. Okay, so maybe you see that this 3-leaf vertex. So what about this number, right? Okay, so there's one example in your textbook, okay, where you can apply this formula here. So the question read like this: suppose that someone starts a chain letter. Each person who received the letter is asked to send it on to 4 other people. Okay, if you read it, you send it to 4 people. Some people do this, but others do not send any letters. Okay, this is real life. How many people have seen the letter, including the first person, if no one received more than 1 letter? And if the chain letter ends after there have been 100 people who read it but did not send it out. Okay. And then how many people send it out? Okay. So how do you compute this? Right. So the claim is you can use the theorem above. So to use the theorem above, you need to make it a tree first, a full enumerable tree. So why is it a tree? Because it says that if no one receives more than 1 letter, okay, so you can make it a tree. And then every person have to send to 4 person after you read it. Okay. So let's say like first one read it, okay, send to 4 person. And then the second one read it, send to another 4 person. But maybe the second one didn't send, and then the third one sent, and so on. Okay. So this is a full. Yeah. So what number are given? 100 people who read it but did not send it out. Okay. So this 100 people is what? Internal vertex or leaf? Leaf. Okay, because they read it, they didn't send it out. Okay. So you got 100. So you got M, you got leaf, then you can compute what? You can compute internal vertex. This one is the target. You can get internal vertexes and also vertexes, right? Yeah. So internal vertex mean the people who read it and send out the letter. Vertexes mean people who read. Okay, so people who have seen the. Okay. So only from two two from two condition you can get other information. Okay, as long as you are a full memory tree. And so we assume if you read it, you must send it to 4. You cannot say you read it, you only send it to 2 or 3. That one doesn't work. So when you read it, have to send it to 4 immediately. Only this will work. Must be uniform throughout every person. If not uniform, then this theorem doesn't work. Okay? Okay. Any question? No. No question. Good. What? Yeah. Okay. 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 Um. Okay. Next. Okay. Next, we talk about the level level of the root. Level of the trees. Okay. So the root, we will start at level 0, and then the child will start with level 1. So it's actually the length of path from the root. Okay. So next we will have level 2 because it is length 2 path from the root. Okay. 1, 2. So here is level 2. Okay. And then so the level of the vertex, the level of the vertex is the length of the unique path from the root to the vertex. Okay. So to get the level of the root, level of the vertex, you just count the length of path you need from the root. Yeah, make sense? Okay. So next is the height of the root, height of the trees. The height of the tree is the maximum of the level. Okay. So for example, this one, the height is 2. So it's the maximum number of the. So in other words, the height of a rooted tree is the length of the longest path from the root to any vertex. So it's the longest root is your height. Make sense? Make sense? Okay. So the height is the maximum level. Okay. Okay. Then next we talk about when is it the tree balance? Okay. So the tree will be balanced if all the leaves are at h or h minus 1. At h or h minus 1. So h is the height of the trees. Okay. So if you have leaf at maybe h minus 2, then this tree will become unbalanced. So maybe this tree will fall down. So you need to make sure all your trees is either at the height or height minus 1. So the tree is balanced. Okay. Does this one look unbalanced or balanced? Okay. Yeah. Okay. So yeah, so if you have trees at h minus 1, then it's h or h minus 1. The tree is balanced. Okay. Next. Okay, maybe this one need to spend a bit more time. This one is the tree traversals. So how you go through every vertex systematically. Okay. So the first way is the universal address system. So universal address system, what you do is you label the root as 0, and then your child by 1, 2, 3, 4, 5, 6 up to k from left to right. Okay, left to right. And then you label, for example, the child of 1 to be 1.1, and then 1.2, and then 1.3. Okay. And then you can keep going on. What you do is if 1.1 got a child, you will have 1.1.1, 1.1.2. And then you can keep going on 1.1.1.1. Okay. And then how you label, how you order them. So you start from 0, 1, 1.1, 1.1.1. Okay, like this. Maybe I just use this picture. So how you order uh, this vertex? So you start with 0. Okay, 1 is greater than 0. 1.1 is greater than 1, and then 1.2 is greater than 1.1. 1.3 is greater than 2, then 2 is greater than 1.3, and then there's one thing you need to note is, for example, let's see. So for example here, okay, so let me write out the sequence here. Uh, so so for example, up to 3.1, right? Then we got 3.1 is less than 3.1.1, that which is less than it's less than 3.1 or 2.1. Okay, so you need to go down here and then go here and then go up. Make sense of it? So, okay, yeah, okay, okay. Any question? Okay, so next. So the procedure for systematically visiting every vertex of an ordered rooted tree we call a transversal algorithm. So apart from this universal address system, because any tree I can do this. Yes. The next one is what we call a pre-order transversal. So pre-order transversal. So what is pre-order transversal? So suppose you got a ordered rooted tree with root R, and if T only have one vertex R, then we just call R as the pre-order transversal. Okay. Otherwise, suppose you got n trees, okay, from left to right. So the pre-order transversal means you need to visit the root first, visit the R first, and then transverse the subtree, the left subtree, and then transverse the right subtree, and then so on. Okay, so what does this algorithm mean? Let me show you the example first. Okay, so let's say we got this tree here. So how to do this pre-order transversal? Okay. So what you do is you uh, first you visit the root first. Okay, visit the R first. So you visit the root first, and then you transverse the left subtree and then transverse the right subtree. Okay, I wrote it down here. This is the procedure. Okay. So you first visit the root first, and then transverse T1 and transverse T2. So what you do is you visit the root first, and then transverse the right left subtree, and then transverse the right subtree. So what you get is okay. So let me draw the left subtree. So the procedure is visit the root, transverse the left subtree, transverse the right subtree. Okay. So visit the root first, we'll get A, and then transverse the left subtree. When you transverse the left subtree, you repeat this process. So transverse the left subtree, you visit the root first, and then transverse the left subtree, and then transverse the right subtree. Okay, you need to repeat this process every time until you get a vertex. So when you get this B, visit the root B, and then transverse the left subtree, and then transverse the left subtree, we need to transverse the right subtree. Okay, maybe I show you another example again. So let's try this example here. Okay. So let's use pre-order transversal. Okay. So the procedure, the first step is to visit the root. So you need to memorize the term here. We see the root and then the left subtree and then transverse the right subtree. This one is important. This one will be okay. So you need to memorize this term here. You need to memorize this. So we see the root transverse the left subtree, transverse the right subtree. Okay. So let's see how to use it. So first you need to visit the root. Okay. And then transverse the left subtree and then transverse the right subtree. Okay. So visit the root, you will get a. Then you need to transverse the left subtree. So when you transverse the left subtree, you need to visit the root and then transverse the left subtree and transverse the right subtree. Okay, so you get B. So when you transverse the left subtree, you need to visit the root. Okay, so you get E. And then you transverse the left subtree again. So you get J. Okay. So after you transverse the left subtree, you need to transverse the right subtree. Okay. When you transverse the right subtree, you need to visit the root again. Okay. Visit the root again. And then transverse the left subtree and then transverse the right subtree. And then go here. Okay. So and P. After you transverse the left subtree, you need to transverse the right subtree. Okay. So you get F. And then after you transverse the left subtree at B, you need to transverse the right subtree, C. And then if you transverse the right subtree, you need to transverse the right subtree. So when you transverse the right subtree, you need to visit the root first. Okay. You transverse the right subtree, left subtree. When you transverse the left subtree, you need to visit the root again. So G. And then you transverse the left. And then you transverse the left subtree, H and M. And now, okay. So let's check the answer correct. Okay. Any question on this algorithm here? No? Following. Follow? Okay. Others, eh? Others follow or not? Yes, ah. You just come in now. Oh, you learned this before. Oh, no wonder. Okay, okay. I learned this before. In what class? Ago, ah? Oh, okay, okay. And then we can end this class earlier. 2 days ago, ah. Oh.
Possible data structure, also learn tree, also learn business.
I see, I see, I see, I see. Okay. Then we can finish this class earlier. And so you learn this in order transversal. Post order also learn. Oh, everything learn already. So weird one, huh?
Like here you take
Okay. Okay. I don't know if the same method they teach. Is it how they teach this? This is the first time I'm also deal with this. Oh, you guys did this before. Oh, the teacher said root left, right. Okay. Okay. Oh, yeah, right. Okay. Yeah, correct. Oh, you guys did this before. Yeah. Okay. So there are three way of order transversal. One is pre-order. Second is in order. Third is post order. So the difference is just when you visit the root. Okay. So if you transverse the left first and then visit the root and then transverse the right, then it's in order. Okay. If you put the visit root in the middle, it's the in order. If you do the visiting order, visiting the root at the end, then it is post order. So you want to go through example? Huh? Yes, in order or post order? Both, huh? Okay, both. Okay, since we got a lot of time, we just do a lot of time, I think. Okay. How about you want to do it now or you want to take a breakfast? Take a break. Okay, take a break 9:52 and then we come back and do in order and post order.哎
，tree 算 graph，
去上，
算 graph，就是
是其中一种 graph
下周 quiz 会
哦不会，我的 graph 的意思是那个 graph and tree 的 graph。
就是没有上次发邮件，不是那个还学什么专业分
啊，对，那个那个，
就是从那个
是 partial ordering。
到底是从他说的开始还是patient？
黑色 diagram 在 partial ordering 里面。
是反正是从 partial
啊，也对，没错。
但是好像你刚刚
这样
好像有画错，
我哪里画错？
哦，我有 P，
哪里 P？
NOP，
NOP？
哦，这是你的 P， 哦，看错了。
你们几时学啊？
就上周，
上周。
上周左右。
哎，你们有学那个 prefix form 吗？有吗？哦，我把那个丢掉，我感觉很奇怪那东西，我不知道有没有。
如果是学 stat 吧，
啊 ，prefix form。
也要花一种找车来做一个 prefix 啊
OK，
就是选一个
啊，没有，它也有那个 prefix form 好像。对，
这个 n 等于 i 加这个 i 是啥
I 是那个
？internal
internal 对，
这个 internal vertex 是指啥？
等下就是没有，哎，有孩子的点，
有孩子的点，
对，
这个也算，
算，还有，
只要有孩子就算。
对
六的是没有，
哎，就这样，
六的
不是没有父母没有孩子，那个是 internal，这边是 live，
啊，没有孩子是六。
跟孩子这边先。
我想问一下，这样理解这个 in order，就是我先从左指数的左
哎，这是你写的啊，你做的啊，
是
我的，哦，抄我的，还没有解释这个，OK，然后继续，
哦，还没解释，
继续
那我待会看吧。
哦，OK，看这，OK，你是学过是不是？
我好
他
像
学习，
没什么印象。
他们说，不是我们，不是这堂课，是另一堂课，他们说，
这个学了就忘了。这个，那我还是说一遍吧。
啊，你说，
这是从就是左指数最左边的这个例子开始，然后便利完小的指数，便利大的指数，便利到这个 root 后就开始根据那个 pre-order 的便利数。
现在
说 order
in order 的话是 transverse the left subtree first，然后你再 visit 那个 root，visit 那个 root，然后你再 transverse the right subtree。
就是如果是多个，就是不止两个的话，
对，
就比如说这有3个，那我是走完这个，走到这里，然后再按这个 pre-order 的顺序，先走左边这个，再走右边这个顺序。
这们两个是不同的东西。
我知道，就是我的理解是这边相当于多走一边，就是从这里这样走，先走到 root，然后再按 pre-order 的顺序，就是这样。
什么叫做按照 pre-order 的顺序走？
就我走到 root 后，我就先走左边的指数，再走右边的指数。我觉得最后肯定是要到底下例子，它这个 root 指数中间的过程。
啊，对。我想一下，不清楚怎样讲。首先这两个是不同的东西啊，你知道不是？但是所以意思说你不可以用这一个来解释这个，对。但是我现在不清楚你想要讲的是什么。
那要不老师你给我讲遍这个的过程，就是具体过程。
这个过程啊，
就如果是上面是3个，底下是这样的话，这个应该怎么讲？
你看啊，这个，对，你应该要从第一个数首先走了，才去走那个走你的 root，然后再继续走其他数。所以你应该要先走这个数先，然后你再去它的 root，然后才走这些。但是你在看这一个的时候，你又要再看它的 subtree，然后再看它的 root，再走其他。
就是对于每个指数来说，都要先看它的 subtree，然后再看 root。
看它的 left subtree，然后看它的 right subtree，然后才是 right subtree。可以吗？等一下我们会做一些例子，给他们做例子。对，
是这样。
就这个 degree 是怎么数的
degree。哦，这个 degree 是这个的定义了。OK，说，对，那个够了。The degree of region is the number of x on that degree. OK，所以你看啊，比如说这一片 region 嘛，对不对？是这整个东西哦。OK，然后它是说 number of edges on the boundary of this region，所以你要算1、2、3、4、5、6、7哦，所以这边是7。
哪里有7啊？
对，你来，那个1、6、7。
哦，就有0。
对，
就是要首尾相连。
该是要。
那不应该这样 ，number of edges。那如果就是单从这个定义上来说，不应该是6。
可能要看这个 boundary of this region， 你 boundary 怎么分？它 boundary 其实要这样分，
哦，
你明白吗？
相当于是
你看这个的 boundary 应该要这样分，
就是要形成一个 circle 的，
Yeah
就反正是 boundary，它必须就是 circle，然后所以说要首尾相连。
the hello. Hello. Let's start. Let's start. Hello. Hello. Testing. Hello. Okay. Okay. So uh, so in pre-order, we visit the root first, transverse the left subtree, and then transverse the right subtree. So in order transversal, so what we did is we transverse the left subtree first, okay, and then we visit the root, and then we transverse all the right subtree. Okay. So let's try the example. Okay, try this example here. So what's in order transversal here? So let me write down. So in order. So one is transverse the subtree. Two, visit the root. First the right subtree. Okay. So depend on where you place this visit, they will call it a different name. So if it is at 1, we call it a pre-order. In the middle, we call it a in-order. If it is the last one, we call it a post-order. Okay, now we do the in-order first. So in-order means you transverse the left subtree, okay, visit the root, transverse the right subtree, okay. But when you transverse the left subtree, you need to transverse the subtree, left subtree, left subtree, visit the root, and then transverse the right subtree. But to transverse the left subtree, you need to transverse the left subtree, and then visit the root, and then transverse the right subtree. Okay, so only until up to the one vertex you can start. Okay, so you start with J. Okay, so you transverse the left subtree, visit the root. Okay, and then transverse the right subtree. Okay, but to transverse the right subtree, you need to repeat your algorithm again. Transverse the left subtree, visit the root, and then right subtree, and right subtree. Okay, so you get n. Okay, transverse the left subtree, visit the root, and then transverse the right subtree. So after you transverse the left subtree, you need to visit the root, and then transverse the right subtree. Okay. After you transverse the left subtree, you need to visit the root, and then transverse the right subtree. And then transverse the right subtree. So to transverse the right subtree, you need to repeat this again. Transverse the left subtree, visit the root, and then transverse the right subtree. So to transverse the left subtree, you need to transverse the left subtree, then visit the root, and then transverse the right subtree. So you have L, G, M. So after you transverse the left subtree, you need to visit the root, then transverse the right subtree, which is H, and then you transverse the right subtree, which is I. Okay, so I think you are done. Okay, any question? No? Still want to do post order or not? Still want to do post order or not? Cannot. Okay, do one more. Okay, not that this is the same tree. We use the same tree but produce different ordering. Okay, next we use post order. So post order, when do you visit the root? Which step you visit the root? Huh? Plus, okay. So the last step you visit the root. Okay. So what you do before is you transverse the subtree, transverse the right. Okay, just to confirm. Let me see. Yeah, okay. So if you want to go back to check your precise definition, you should go back and check your precise definition. So you start with T1, T2, Tn, and then end with precedent. Okay. Okay, so let's start. So transverse the left subtree, then transverse the right subtree, and then visit the root. Okay. So this one we need to transverse left subtree first. So we want to transverse left subtree. That means we need to transverse the left subtree first, and then transverse the right subtree, and then visit the root. Okay. So to transverse the left subtree, we need to transverse the left subtree, and then transverse the right subtree, and then visit the root. Okay, so here can stop already. So we start from J again. So traverse the left subtree, next traverse the right subtree. Okay, to traverse this right subtree, you need to start this algorithm again. Traverse the left subtree, traverse the right subtree, and then visit the root. Okay, so what we get is N P, and then visit the root last. Okay. So after we traverse the left subtree, traverse the right subtree, we need to visit the root. And then after we traverse the left subtree, we need to traverse the right subtree, and then visit the root. So we got Fn. After we traverse the left subtree, we need to traverse the right subtree, which is C. After we traverse the right subtree, we need to continue traverse the right subtree, and then to traverse the right subtree, we need to start this process again. Traverse the left subtree, and then traverse the right subtree. And then to traverse the right subtree, we need to traverse the right subtree, and then left subtree. Okay. So that means we got L, M, G, okay, and then H, and I, and then visit the root. Okay. So we already visit, traverse all the left and right subtree, and then we need to go back to the. So the root is the last. The main root, not the subroot. All right. Okay. One question. One question. Okay. Okay. So these are reading the roots. So there's another way. If you do a lot exercise enough, you can use this method to help you find it out. I won't explain it. You can read it in your textbook. Just using this line. There's a different way to read this line to get the tree or the transversal. I won't explain it, but you can read it. Okay, next we want to find. Have you learned spanning tree? No. Okay. So now we want to find an object called spanning tree. Okay. So you can think of it as a backbone of you. Okay. Human. Yeah, okay. It's like a backbone. So spanning tree is a tree that contains every vertex of the graph. Okay. So for example, if your graph looks like this. Okay. So one of the spanning tree could look like. But the spanning tree may not be unique. So maybe you can find another spanning tree like this. Okay. As long as you contain all the vertex and then you connect them, it's a tree. Okay, this is a spanning tree. Okay, spanning tree. All the vertex and then you connect them. So a simple graph is connected if and only if it has a spanning tree. Okay. Is this clear or is it true? So you got a simple graph, they are connected. So all the vertex are connected, then you can build a tree because you can pick all the vertex and then form the path. And then if you have a spanning tree, if the graph have a spanning tree, that means you can reach every two vertex with a path. So it is connected. Okay. Any question? No? Any question? No? No? Okay, next. So next we will find the spanning tree. Okay. So give you a graph, how to find the spanning tree. Okay. Give you a graph, is there an algorithm to find the spanning tree? So first is using the depth first search. Okay. So in a moment we'll see why it's called depth first search. Okay. First, what you do is you pick a vertex of the graph. Okay, give you a graph, you pick a vertex. And then next, you start drawing path by adding vertex and edges adjacent to this vertex. Okay. Okay, let's show you this. Okay, let me explain using this example. So let's start with a graph here. Okay, G. Okay. So this is not a tree, right? Because you have a. Why is this not a tree? Why this G is not a tree? Yeah, you got a simple circuit. Yeah, so this is not a tree. Okay. So let's find a spanning tree using the depth first method. Okay. So you pick one vertex, any one you pick. Okay, let's say we start with F. Let's start with F. So you draw add vertex and edge that's connected to F. So for example, G is connected to F, so we draw to G, draw to H, draw to K, draw to J. Okay. But you found that there's no place to go now. Okay. But it is still not a spanning tree yet. Okay, haven't reached all the vertex. So what you do is you go back to the last vertex that is adjacent to a vertex you haven't visited. Okay, so you go to J. Okay, you backward, back until H, and then you move to I. Okay, and then you stop here again. But you still haven't reached your spanning tree yet. Okay, because you haven't touched all this. So you need to go all the way back to F and then grow again. Okay. So you back to F and then you can grow to D and then grow to E, grow to C, grow to A. And then D you haven't reached yet, so you go back to A, go back to C, and then you go to B. Okay. Okay, let's try another example. So for example, which vertex you want to start? Maybe we try one example. Which vertex you want to start? Pick one vertex and then we try start. Pick one. D, yeah. D, huh? Okay. Let's start with D. Okay. So we start with D. So the algorithm says add all the vertex that is edges and vertex adjacent connected to D. Okay. So for example, one way we can do is we can go to E. Okay. And then we go to C. Okay. And then we go to A. So we go from D, E, C, A. Okay. But we haven't visit B yet. So we need to go back to C and then go to B. Okay. And then who else we haven't visit? We haven't visit F yet. Okay. So we need to go, I think depend on you. You want to go all the way back to E or you want to go to B? Last cannot depend on you. So the last one, so you need to go to E first. Okay. From E, you need to go to F. Okay. It's the last vertex that's adjacent to the vertex you haven't visited. So you have to pick E. So you have to pick E and then go to F. Okay. And then you can go to G. Then maybe you can go to K and then go to J. Okay? And then you realize that you haven't visited I yet. You need to go back to the last vertex that you is adjacent to this I. Or you need to go back to H and you draw that. Yeah, so this is another spanning tree. Yeah. So this spanning tree in this graph will looks like so you throw away this line. Then for this one, you throw away different. You want One? Oh, okay. So green lines, okay. The spanning tree that we just draw looks like this. Okay. How about the figure 7 one? So figure 7 one, let me draw it out. F G H and I. Okay. So the difference of them is like this two lines. Okay. So if you yeah. So these two produce a different spanning tree. Okay. Okay, so this one is breakfast. Next is breakfast. Okay. Breath is the white. So this one will grow wider. Okay, let's see why it grow wider. So first we choose a vertex again. We choose a root. Okay. And then we add all the edges that is incident to this vertex. Okay. So we don't just add the edge and vertex, but we add all the edges that incident to this vertex. And then we keep going on for every vertex you have. Okay. Okay, let's see the example. So let's see the example here. So let's start with E. Okay. We start with E. Okay. And then what we add is all the edges incident to E. We add. We don't just now we just add one, right? Keep going on. But now we straight away add all the edges incident to it. So for example, with E, we add B, D, I, and F. Okay. Add four of these. Okay. We add four of these. Okay. And then for each of these, we add all the edges that's adjacent to B. Okay. For example, adjacent to B, we have C and A. Okay. A and C. And then adjacent to D, we have A and H. So we add H here. So the question is, why not we connect D to A? D is connected to A, right? So why not we connect D to A? Huh? Yes. So if you connect D to A again, then you will have a circuit, which is not a tree. Okay. So since B is already connected to A, so we just need to connect D to H. It's enough. Okay. And then similarly, you can draw F to G, F to I, and then so on. Okay. Okay. So maybe we try use this method to find this spanning tree again. Okay. So maybe let us start with H, F again. Okay. So let's start with F. So we use breadth first search. See what we get. Okay. Search. So it's that first, right? So now it's breadth first. Okay. If we start with F, what we have is we need to connect all the edges adjacent to F. So we got G, we got H. Right? See? These three. So we add it in. So how about who are adjacent to E? So you got D, you got C. Okay, so you need to add your C and D in. And then who is connected to C? A and B. So connected B. How about D? D is B and F. BD is E and F, but you don't need to draw this again. Otherwise, you will produce a simple circuit, which I don't want. Okay, G connect to who? G connect to F. Okay, and F. But I don't draw this because I will produce a simple circuit. Okay, so G done. How about H? H connected to I and K. So I can draw I and K. I connected to H again, and then K connected to J. Okay, so you can see that. Let me move. So what's the height of the depth first search? What's the height? Height equal to what? 0, 1, 2, 3, 4. Height is 4. Okay, how about height of this? 0, 1, 2, 3. 3, right? Okay, so this height is 3. So you can see that this height is generally larger or equal to the breadth height. Okay, and then you can see this breadth, the wide, you got three children. Like, is it wider? This one is wider. So this one breadth. So this one general will grow wider. General. Yeah. Say again. D. D, huh? Oh, yeah, right. D connect. Yeah, correct. So this D actually have to. D is, yeah, so here, so now you got 4 children. Yeah. Okay. Yeah. Okay, correct. Yeah. Because D is connected to F. So you got 4 children. So you grow wider than the breakfast. Okay. Any question for breakfast and breakfast? Question? Breakfast. Yeah. Okay, next one is minimum spanning tree. Okay. Last time we talked about the idea of putting number on the edge, which we call the multiplicity of the edge. Okay. Or this time we call it the weight of the edge. Okay, so we can put some number on the edge. Okay. So if um if after you adding up, after you can obtain the spanning trees, okay, and then with add weight on the edges, if you get the smallest possible sum of the weight, then we will call it a spanning tree, minimum spanning tree. Okay, minimum meaning the smallest possible sum of weight of the edge. Okay. Uh, So we will introduce 2 algorithms to do it, okay? And then we call these 2 algorithms greedy algorithm, okay? Why are they called greedy? Because each step, we want it to be a optimal choice. And then in the end, it still produces an optimal answer. This is called greedy. Because in general, if we do it optimally every time, it doesn't mean that the whole process is optimal. Okay, this is not true in general. So it doesn't mean that if you do optimal at each step, your whole process turn out to be optimal. But in this case, these 2 algorithms can produce the optimal solution. Okay, we won't prove this, but let's see how to use this. So everyone get the goal or not? So let's say our edge got weight. After you pick the spanning tree, you need to determine whether this is the minimum sum of the weight. Okay. Okay, let's describe an algorithm and then see one example. So one algorithm is called the Primes algorithm. Okay. Primes algorithm says that if you start with any edge with smallest weight, okay, just pick one smallest weight edge with the smallest number, and then you add to the edge of the minimum weight that is incident to a vertex. It's already in the tree. Okay, but don't want to form a simple circuit because we want a true. Okay, stop until n-1 edges have been added. Okay, because tree had n-1 edges. After n-1 edges added, you got the tree. Okay, let's see how this works. Okay, so for example, now you got a weighted graph. Okay, meaning the edge you have number. Okay, there are a lot of spanning tree you can draw. Which spanning tree have the least sum? Okay, so this algorithm will tell you how to do this. First, start with the edge with the minimum weight. So how many minimum weight here? So the least one is weight 1. So you have CD, KL, and BF. Okay. So let's follow this example first. So let's start with BF. Okay. So anyone you pick, algorithms say anyone you pick will work. So let's start with BF. Okay. Then what you do is add vertex that has minimum weight. Okay. Adjacent to the existing vertex. So for example, B. Okay. If you want to go from B to A, okay, or B to C, which one is minimum? Okay, so if you go to B to A, you can go which way? You can go this way or you go the other way. Okay, but this is the minimum way. So you add BA. Okay, and then F, you can go to FJ. You can go to FE. You also can go to FG. Okay, so which one is the minimum one? Huh? FJ. Okay, so you can add FJ. Okay. And then what you can do next, because next you can continue with J and A, F as well. So what you add is you add AE. Okay. You don't want to add FE, right? Because FE is 4, but AE is just 3. So you will add AE. Okay. Make sense or not? Make sense? Okay. And then what you do next? So how about I? Do you want to add EI or you want to add IJ? IJ, right? Because if you add EI, this one is greater than IJ. So you will add IJ. Okay. And then next is G. So now you only have, let me draw what you have. So you got EF. Okay. Next, how to go to C or G? Go to C. Go to G. Okay, maybe you can go to G first. How to go to G? Huh? This is the fastest way, the least way. Okay. How about go to C? Go to C, got two way now. You can go BC or GC. Right? Which one you want to pick? You will pick GC. Okay. And what else? K, you can go to K. Want to go to K? You want to go K first? Yeah, okay, you can go. Maybe what they go. So they pick C, G, then they do. So you can go C, D, maybe, and then G, H. Okay, never mind. Let's say we do our own example, okay? Let's try our own example. So this one, it claims that this is the least one, 24, okay? So if we start with our algorithm, we should also end with 24 again, okay? So let's start with different one, okay? So let's try our own example. Let's try our own example. So let's say, okay, which weight you want to pick? C, D, B, F, or KL? Okay, maybe don't pick BF anymore, they pick CL. So choose C, D, or KL. D, okay, okay. Let's do CD. So we start with CD, weight 1, okay. What's the next edge you want to pick? How about the next one you want to pick? FG, and GF because G equal to. I want to pick. Huh? FB. Okay, because CB is 3, FB is 1. So you must pick FB. What else? A, can. Sometimes you got a freedom, sometimes you don't have freedom, okay? B. EF, this one you don't have freedom. So EF is 4, AE is 3. So you have to pick AE. Okay, what else? FJ. Okay, yes, FJ. J. How about next? AI. AI. JI, correct. Okay, JI. Because EI is 4, so you must pick JI. 3 more points. GH. GH, yes, correct. So you must pick GH because DH is 5. There's only one way to do it. GH. There's only the least way to do it. Huh? HL then LK. HL then LK. And is HI, HL, H3. Yeah. So that's, huh? What do you get? Same. So this one is 3, this one is 3. So how many 3 you have? You got 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So this one is also 24. Yeah. So you also got 24. As long as every time you add 3 edges of minimum weight that's incident to the vertex already in the tree, then it will work. Okay. Any question for this part? Yeah. Oh, okay. So the next one is a Kruskal's algorithm. So this one is easier. So you just also start with any edge with smaller weight. and also add to the three edges of minimum weight, but no need to be incident to the vertex that's existent before. Just add all the minimum one in first. Add until you got the three. Let's see the example. So minimum one, they start with CD. Okay, start with CD again. And then they add all the minimum one first. So for all the one, you add it in. Okay, just add it in. One, add all the one in. And then next, add all the two in, as long as you can add it in. So add two in, add two in, add two in. Okay? But you still haven't formed the tree yet. Okay? So add all the three in. Add as long as you can add them. So three, add it in. Add three in. Add three in. Add three. So you can notice that they have a choice here. Okay? You can't add these three in. If you add it in, what do you get? A simple circuit. Okay, so some of the tree you don't want to add it. Okay, and then since you already connect all the vertex, then this tree is done. Okay, so there is some freedom here. Maybe you say I don't want to add this tree in. Okay, I also can add this tree in. Okay, but anyhow you do, you still produce a minimum spanning tree. Okay, actually I can't add this in because this one will form a tree. Maybe you can see. Okay? Yeah, there's some freedom there, but no matter how you play with it, you have to you will also reach the same minimum weight standing tree. This is what this algorithm shows me. Why is it true? What the book was saying about it. But anyway, this algorithm will always produce the minimal spanning tree, but not necessarily unique. Okay, you can produce different minimal spanning tree, but they have the same. It's not unique. The algorithm is not unique. Okay. Any more question? No? No, maybe we take a break. Take a break. Come back 10:45, and then we do tutorial. If finish earlier, then we can finish earlier. Okay. Oh, that's, I thought you calling me, huh?
Oh, I thought you're calling me.
Oh. Okay, thank you. 啊，
为什么不可以就直接一个位就到？然后就只可以。
有时候我听到可能比较难治疗，可能可以，但是比较难治。我觉得
先把大的看最大的，然后看有没有合适的，然后最大的就是把最大的拿掉之后算一遍路，再把第二大的整掉，再算一遍。最大的相对比会比较短。就是因为从最小的推
最大推也是
对。
我不他有这种端的，应该是这么多块，他应该是能够证明他是最小的。但是你如果从最这个小，不知道就比较好。既然你不懂呢，但是他肯定他应该是可以证明到，不管你是哪一种，如果你从大的做到小，这个块小而已。
不可以把这个画上去，
要把这个
就跟这种一样。我是想这个对，
你就写一个调，
画成个圈之后就直接从就到的那个车里。
哦，但是问题是你这个本身是一个腿，
对啊。把它换成一个那个。
你说这个 graph 本身，换成
把它找了。
把它打开，
对。对。
但是你有 circuit 就是那个说，比如说 F 啊，但是你就有很奇怪的东西。
对
呀，对呀，有 circuit，
我们可以没有Discrete。
我懂。
是哦，对。
怎么这样？
是，我想多了。是我们可不可以在它形成那个变成 circuit 之前，把它这一个stop tree 里的最大的删掉？就比如说从 F 开始，它的一个 stop tree 不是 F B A E F， 然后我们看 F B A E F 中最大的是E 到 F， 所以我们把 E 到 F 删掉，我们直接不考虑这个。然后我们再看这一些，它还是 F J F J I E F， 然后我们把 I E 或者是 E F 删掉，它也不会生成那个 circuit。然后 因为我们最后找的那个 path， 它肯定不是一个 circuit， 对吧？所以我们只要从这里开始，只要会形成 circuit， 我们就把那个 circuit 删掉，circuit 里最大的那条路删掉，然后是这样形成那个 tree， 我们是这么认为的。
你是说看完所有的 circuit， 然后把那个 circuit 最大的删掉？
最大的那个 path 删掉。就比如说，这4条那个 path 里最大的是4，我们把4删掉，然后这就是其中的一个 sub path。
我觉得可以，但是问题是你在 form 这个 circuit 的时候，你有没有一个比较系统性的看那个 circuit？你只要看，因为它这个图它只是四方形嘛，但是有些图它可能三角形哎，然后怎么行呢？你要怎样能够系统性的看这些 circuit？难道那你是要看这整个 circuit 呢，还是你要看这个 circuit 呢？还是
可以都看，就是
都看都要看，全部都要看？
因为我本身我们把这个图变成一个 tree 的时候，就是都要看。
对，但是你在想啊，你看啊，如果你这里所有都是3的话呢？如果你 circuit 里面所有都是3，那你要丢哪一个？
就这一个明白吧？
这个丢其中一个。
就是把一个丢掉，然后看剩下的能不能形成 circuit，不是剩下的还能不能形成 path， 或者是然后如果都能形成 path 的话，再看它能不能形成medium。
啊，你要看一下，对，你要看一下，对，对对对。哎，
吹是这样的，
对
这个是穿 L，这个是穿 left， 这是穿 R，
对，
就是
对他们的那个看法是这样，你可以回去看他那个最原始的那个 definition， 我那个只是一个 summary 罢了。你看他在看这个 right 的时候啊，对，先看最原的最有的，你看它是 start with T1，哦，它是 root，然后 T1，然后 T2，然后继续 OK，in order 比较清楚，你看它是 start with T1 root，然后再接下来的，所以它就是所有的 right 都在
哦，
啊
那个 left top tree 只有一个，
耶，对，
就比如说4个的话，就只是一个，
耶，
然后 R 可能 L 就只有一个，R 就是剩下的。
没错，没错，啊，你要回去，如果你要问这种问题，不是你要回去看那个原始的，
其实就是这样说 left right 不太准确。
啊，不太准确，但是也可以。对，不太准确。如果要准确一点，是要说 leftmost 上去
leftmost
啊，然后最 left，然后就 right，
就直接 right。
啊对对，是不是？
嗯，
哎，
找最很小的那个就一，然后3，我选3，然后这2个为什么要接起来？这2个
你要 tree 啊，啊对对对，对，没有错，没有连到嘛，对不对？全部，
因为这个2个连的，
没，我们还是在早期，
这个我们如果选 F 开始，
好，然后
然后我们走这里1，2，然后
这个什么？
这个你一定要start with minimum weight 的 H
这样我选这里哦。
CD 哈，
然后 CD，然后1，然后2、3，然后这里不难的，这里3，
你是说这个加起来不是24号？
是不是？我觉得他的律师很不明白这个那个
怎么找
怎么找
？OK，你就是 OK， 你就是OK， 这个 prime 的意思说你 start with 那个 minimum weight， 然后你再加 minimum 的 H such that 它是incident 去之前的原本，
连着一起走。
对，它一定要连在一起走。所以意思你看啊，
这里就不能下去，是吗？一定要
对，所以这个怎么说呢？你看啊，你从哪里去哪里找？
从这里开始，1、2、3，然后1、2、3，然后到这里。
OK， 到这里，然后你要加剩下的东西，对不对？OK， 假设你要加剩下的东西，就是你看啊，谁可以去 F， 谁可以去 E， 这些点都可以去 E 嘛，对不对？最靠近的就是它嘛。如果 F 去 E 的话是4步。啊，对，它就是 K 了，这样也不要，这样就不可以了，这样就不可以这个。对，就不是不了了，所以应该要讨论要不要去 I。OK， 要讨论要不要去 I。OK， 所以你看，E 去 I 是4步 ，F 去 I 是5步。啊？F 其实不能去 I 了，它不能一步去 I， 我就说 ，OK， 它要这样子去 I， 但是你可以先让 F 去 J 先哦，或者你可以先讨论 J 先。
是这样子是，然后我要去 I， 然后这里是4，这里是5最低的。
对，这样应该是不可以这样看的。所以你要在想，你要不要去 I 先，对不对？
所以不要去 I 先，这样我就先接 F 去 J 先。
等一下，你等一下。老幺。
老啊，老师，我已经太老了，叫3倍。
他 friend 就开辣的，就是
有想下啊？我觉得呢，我觉得有干的有很明显。我觉得你看啊，你一定要把 BF 处理掉先。
先处理掉 F。
比如说你这个 CD 啊，你可以先把 CD 处理掉。OK， 不然我们玩试下。我觉得啦，给我试下，来试一下，来试一个东西。假设我们要跟着那个，我觉得这个好像没有跟到，还要试一下。所以我们从 CD 开始跑 ，OK， 然后 C， 这应该是最低的 ，OK， 我试一下跑吧。会不会太大？等下看一下，
3、啊，
2加4的话，
28啊，这个不可以，6、9、27、28、24啊，对，这个不可以。我看一下啊，再来一次。这边。哦，这个也是最小的。这个也是超过了。哎，真的超过。等一下啊。看一下你的，看一下你的，看一下你的。
为什么换这一遍了？我上全是这样子的。
对。然后
然后
你觉得这个不明吗？
我刚才讲的是什么？等一下。
啊。
少一点应该好一些。你可能多了有可能还会下买了那个
你找不到 minimum 是不是？
转到26位。
来，我来复习一下。Hello. Okay. Try to do the tutorial question, and then I got one question. See you guys can solve or not. Okay. Try to do your tutorial question. If you are free, try help me think a question. Think about this question. So, okay, you see that this algorithm, we didn't understand it wrong. So you see the algorithm saying that you add
an edge incident to a vertex already in T, okay, not forming a simple circuit. So let's say just now we start from CD, right? Okay. Start with CD, okay. So the next thing we should add is anything that is minimum to C or minimum to D, right? Okay. Why not we do this and this? Is this what the algorithm suggesting? Okay, let's keep doing this, okay? So to H, we add a minimum weight that doesn't form a circuit. Okay, so we cannot pick GH. So we go HL. How about G? G, we can go FG or GK. But so we go FG because FG minimum. Right? Okay. And then next, I K only one way to do it. F you can go to J, E, B. Okay. So we can go to B because B, FB is a minimum one. How about B? B only can, okay. K go to where? K can only go straight because you cannot go up because from minimum circuit. And then B only can go to A. Okay. And then A, okay, and then J, where J can go? J can go I. Because J cannot go to F. Go to F, you will form a circuit. So next, A to E or B, I to E. So A to E, because A to E is 3. So let's add up 3 plus 2 plus 1 plus 2 plus 2 plus 1 plus 1. So what's this? Hey, 7, right? But this one is not the minimum one. So where's the mistake? Why? Add an H which is minimum. Wait, let me see. An H that is only one, you mean? Also, okay, let's try again. Let's try again. Okay, let's start with CD. Okay, let's start with CD. Okay, there's 2H, 3H we can add, but minimum one is CG. Okay, we add CG. Okay, good. Next one, minimum one, so 3, 4, 5. So we can add one of these two lah. Okay, so any one lah. Maybe I don't want GH, I want FG. Okay, so next one, got 5, got 4, got 2, got 1, got 4. Right? Or 3. But no. I think we have to consider all the vertex. Need to consider all the vertex and then find the minimum one. So we got 5, we got 4, we got 3, we got 2, 4, 1, 3. So we have to pick one. Okay. And then next, this one cannot pick because this is a circuit. So it's 2, 4, 2, 4, 3. Okay, so either one of these two I can pick. So which one? Maybe pick this one. So next one, you can pick 3, 3, 2, 3, 5. 2 again. Okay, pick 2. And then the next one, you can pick 3, 4, 3, 3, 3, 5. So 3. So which 3 you want to pick? Yeah, pick either one. AC. AE, okay. Okay. And then next, we can pick 4. Okay, this 4 cannot pick because it's circuit. So you can pick this 4, pick this 3, pick this 3, pick this 4, pick this 3, pick this 4. So we pick 3, either one 3. It's this 3. Okay. And then next, what we can pick? We can pick 1, 4. Okay, 4 cannot pick. This one circuit cannot pick. So pick 3, 1, 3, or 4. Okay, got 1. So we need to pick 1. Okay.
And then next one, we can pick 3, 3, 5, 4, 3. So pick 3 or either one of the 3. And then this one 3. Okay, let's try this again. This one complete already, so let's compute. 3 plus 2 plus 1 plus 3 plus 2 plus 3 plus 2 plus 3 plus 1 plus 3 equal to 1. Okay, what? Okay. Okay. Yeah, okay, good. Okay, this one looks like an algorithm. Just now we are like randomly pick the X. Okay. Yeah, we didn't consider all the NLP the minimum. So this one, yeah. Okay. Okay. Yeah. It looks like an algorithm. Okay. Yeah. Trying to the tutorial question. Yeah. Question. Anything you want to ask? There you go, question. Huh? Huh? The tutorial question. Discuss with your friend.
那又不是消化，重要啦，重要，划走。Discrete 来又不熟了，那是有。这么天。
手电。
看得到。很高。 啊啊，知道。对呀、我关掉，我关掉。
讲到。
如果你能证明到这个是大于这一分，你还是完美的。但是如果你不能证明到你不能，大于这个。对对，来来来，我看一下。
Yeah. Hello? Okay. Let us quickly run through what you've got is the same. Okay, let's see some pretty picture here. So 10.7.6, this is a planar representation. So you just draw one graph. Wait, hey, sorry. Okay, so 10.7.6, this is a planar graph. So you just draw an isomorphic graph, which is a planar representation. That means there's no edge crossing. Okay, so you can move this edge around. I hope you draw something similar to this. Anyone got something similar to this? 10.7.8. Okay, there are a few ways to show this is non-planar. Okay, one way to show is use the Kuratowski theorem. Okay, you found a subgraph which is K33. Okay, you can see that K33 is hiding here. Okay, so one technique to find it is when you do this planar graph, right, isomorphic. Okay, you can see that you cannot move this thing out. If you move out, you also got edge crossing. So now you can start guessing whether K5 or K33 is inside there. Okay. And then you can try to find some vertex and then try to link them up. And then you will get this K33. Okay. K33. Yeah, K33. Okay. So K33 is here. I put different color here to show you this is a bar-part graph. Okay. So this is the bar-part graph. K33. K33 is here. Or you can use the corollary, then use the formula. Use the formula, this one. Okay. So you can compute the E, compute the V, and then compute 2V minus 4, and then you see that E is greater than 2V minus 4. And then use the contrapositive of the corollary. Or it is non-planar. And then third way, you can use diagrammatic. Okay. I think this one but to use the diagrammatic, you can see that you can move this graph, okay, draw some isomorphic graph, and then you need to argue how to put CD and FG. Okay. So because they are symmetric, so you just need to consider one of them. Okay. So let's say we choose C. Okay. How many places you can put C? You can put C here, R1. You can put it here, R1, or R2, or R3, or R4, or outside. So when you try to put this C in this 5 region, you will see that you cannot avoid edge crossing. Okay, you can go and try. And then you just need to argue for C is enough because for D, G, H, this graph is symmetry, is the same. Okay, so argue 1 is enough. Okay. See that wherever you put it, you cannot avoid edge crossing. 10.7.11. Verify that this one we show that K5 is not planar using the corollary. Okay, now try to use diagrammatic as well. Okay, try to draw some isomorphic graph. Okay, and then try to place this A in different region. Okay, how many region you can put? So you can put it here. Okay, you also can put it here. You also can put it here. You also can put it outside. Okay, so 4 region you cannot avoid edge crossing. You should see it. This one, if you put here, then this one need to intersect. If you put here, you will get intersection as well. Okay, can see it? Can see it? If you try, if you can't see it, just draw it and then draw the line, and then you'll see the section. Okay. Okay. Then 10.7.12 and 7.14, just use the Euler formula, and then they meet some difficulty here, so you need to use this handshaking lemma because you are given degree and not the edge. So to link edge back to degree, you need to use this handshaking lemma. Okay. Handshaking lemma. Okay. Yeah, you cannot directly use the degree because the degree doesn't represent how many edge you have. You need to use this handshaking lemma. Okay. Huh? Yeah, so on. Oh, 6, huh? Okay. Yeah. 6 region. Okay, next one, we can connect. Okay, this one they tell you K connected component of planar graph. So how you build a new formula? Okay. So suppose you got K connected component, right? Okay. Can I make them into a one connected component? How? You just link them. You just link any 2 vertex. Okay. So you need to use K minus 1 H to link K connected component. Okay. Once you link them together, do you introduce new region or not? No, right? You didn't cut anything. So you don't increase the number of region, you don't increase the number of vertex, but you only increase the number of edges. Okay, so you can use the Euler formula again. Because after you add the K minus 1 edges, you form one connected planar graph. So use Euler formula again. Okay. Vertex doesn't change, only edge change. Region also didn't change. Okay. So you get this new formula here. R equals to E minus V plus K plus 1. Okay. This kind of question won't be in this final exam. This one is just good for fun. This kind of question will be final and okay. I try to make the final quite easier this time. Okay. But doesn't mean that you don't study. Okay. 10.8.20. This is not homeomorphic to K33 because this is actually planar. Okay. Actually, planar is not homeomorphic to K33. 10.7.22. This one. This one. And what's this question asking about? Or whether it's homomorphic for K33 or not. It is because you can just draw it. You can draw the subgraph. Okay. Although this you know that homomorphic is linked by a sequence of what's that called? Elementary subdivision. Okay. So you can draw the K3 inside here. K3. 10.7.24. This one is like a cloud. So is this a planar? Okay. If you try to move this out, I think it's impossible. So you should guess there's K33 or K5 inside here. So actually K5 is inside here. Although you can see that there's extra vertex here, but never mind. We only care up to homeomorphic. Okay. So under homeomorphic, this line here is equal to this line. Okay. This is homeomorphic. Okay. Yeah. No matter how many more vertex on the line, this doesn't matter because they are homeomorphic. Okay, 10.8.2. This one, how to color. So you can color the region become a coloring of graph. Okay, this one, Ife, you guys. This one, coloring become a color of vertex. Okay, so the length become a dot. All the connected region become a dot. And then if they share a boundary, you draw a line. So you make it a coloring of graph. Okay. Why is it less than 2? Because you can color it using 2 color. Why is it greater than 2? Because at least 2 vertex connected. So you need at least 2. Because you don't want adjacent color vertex to be the same color, right? Right? Adjacent vertex cannot have same color. Okay. And then why is it less than 2? Because 2 is enough to color the graph. Okay. 10.8.4 also, you can make it into a graph. Okay. Connected length become a dot. And then if they share a boundary, draw one line. Share boundary, draw a line. Share boundary, draw a line. Okay. Then become a coloring of graph. Why is it 2 same argument? Less than equal to 2, greater or equal to 2. Okay, this one quite important. This one. You can see that this, right? You can color with three colors or less than equal to 3. So why have to be greater or equal to 3? Okay. Because you got a triangle. Okay, so triangle here, they are all connected adjacent to each other. So there must be different color. So you need at least 3. Okay. Less than equal to 3 because 3 is enough. Okay. Greater or equal to 3 because you got a triangle. Okay. Triangle all adjacent, you must have different color. Make sense? Make sense? Make sense? Okay, next, for example, this one. Okay, I skip this one. For example, this one, 4. 4. Because if you use 4 color, it's enough to color it. But why is it less greater or equal to 4? Okay. Because it contains a K4 here. Complete 4 vertices graph. Okay. You contain a K4 graph here. Okay. Actually, it is really because of this, you need to add this color, right? When you color it, you see that this is adjacent to this, adjacent to this, adjacent to this. So you need the 4th color. Okay. So this is the reason why you have to add an extra color in. It's the K4. You contains a subgraph of K4. Okay. This one, yeah. I think that's all. This one just also for fun. Okay. Any more question? I think next week also quite short. The lecture would do. But do quiz quite long, I think, because we do combine quiz. I think at least half hour, maybe half an hour should be enough for 20 minutes. Okay. Question, see you next.